Thanks so much, Marissa, for the intro. As Marissa mentioned, you'll be hearing from not just one, but two work units today. We're all working under the same statements of need. Shannon Brown, my co-PI, is unfortunately in the field all week doing some core cam work. So it's just me today, but you'll hear from the broader team here soon. So with that, I will get going. Let's see. There we go. Just a brief agenda. So short on the background, just some motivation, and then you'll hear from Justin and Alex primarily first, and then our group second, and then we're going to leave some time at the end for discussion. And I'll emphasize that feel free to put your hand up or interrupt with any questions as we go. We're trying to keep this informal if possible. So if you have an idea, feel free to stop us in our tracks. And so with that, I'll just orient everybody. This is an image of Manasquan Inlet in the background. This is notoriously hazardous, and they've had quite a few management and shoaling issues there, especially in the past few years. And so this work all is motivated by first Monica Chaston at Philadelphia submitted a statement of need, just highlighting the hazards of inlet shoals, and we need new tools to monitor and track them. And then more recently, Rachel Malberg from the Great Lakes submitted something similar, just asking for essentially more near real-time monitoring capability for these shoals. As most of you know, we spend millions of dollars dredging, and it's very difficult to optimize sort of our survey and dredging frequency and schedules. It's hard to know sometimes, where these ebb shoals even are. We've visited Philadelphia and learned a lot this past year at some of their sites. And so what we can do is, as traditional surveys with vessels are quite costly. They're dangerous, right? They require different vessels. And so here what we're leveraging is the power of satellites in orbit. And so we'll focus on two different workflows today, the multispectral analysis group and then our more wave dominated group. And you can see here, this is the same inlet, Oregon Inlet, close to home here for me. Just a couple weeks difference in time, but you can see the variability in the wave breaking signature offshore here and over that ebb shoal delta, tidal delta. First off, we're going to start with Justin's group, so I'm going to pass it right over to them.
Thanks, Ian. Appreciate you teeing us up for this. So yeah, I'll lead start off with some updates from the multispectral work group. The work that I'm going to be presenting is actually led by a smart scholar, Copeland Cromwell, who's been working with us. He's a PhD student at the University of Florida, and he's on the line and will chime in if we say anything that's inaccurate about his work. But basically what motivates the multispectral side of this, right? And by that, we really just mean using multiple bands from the satellite imagery that's available, right? And so as Ian pointed out in that nice slide with the image of all the satellites that are now in orbit, a lot of this satellite imagery is freely available, as we know, right? Some of it, along with aerial imagery, is just in the simple Google Earth desktop app, and others of it we can pull from Google Earth Engine using, for example, like Python scripting. We can pull that imagery, right? And a lot of it, particularly the Sentinel-2 imagery that we're working with, has up to 13 bands, and we can use those for a variety of applications, and they have been used for a variety of applications in the academic literature. And so for us, what we're hoping to do is develop a set of toolboxes that pull this academic knowledge and put it in a more applied, digestible setting for all of us at ERDIC to use, as well as for the districts. And so what Copeland started with is using the normalized difference water index, which has been applied in the literature quite a lot and is designed, as the name would imply, to help differentiate where there's water and where there's land. And so this has been used, for example, in COSAT, which is a shoreline detection from satellite imagery workflow. But what Copeland found is that, especially because it's using the green and the near infrared bands, it's actually pretty good at detecting like a quasi bathymetry. And you can see this here in this set of figures. We've got 3 different case sites that Copeland and the team have been working at. And those are bathymetric contours kind of in the black pencil line drawings, overlaying against an NDWI image from Sentinel-2 satellite imagery. If you could advance the slide, please, Ian. Yeah, thanks. Perfect. And so, okay, we made this initial inference, right? We've got what looks like a good qualitative comparison between what we see in these NDWI images, right, where we're using the green and the near infrared bands of the imagery together. And so can we take that another step and quantify it? So the first cut that Copeland did at this was to actually correlate bathymetry from topobathy LiDAR with the NDWI values. And so what you're seeing here is a windowed correlation map where the darkest reds and the darkest greens are more correlated. The green is positive correlation, the red is negative correlation. But regardless, what you're really seeing is that inverse relationship there between NDWI values and field measured bathymetry is quite strong over the shallowest features, so our shoals. So we can reasonably detect shoals with this approach. And so next slide, please, Ian. Thanks. Next, we all asked as a team the question, how are we actually going to extract shoals, right? If we just want to gotta send someone a map of, hey, here's what these shoals look like in the plan form through time, so that we can understand, for example, ebb tidal delta dynamics at a particular site, and as that may have implications for dredging strategy, or because our ebb tidal delta bars are often attaching to our updrift and downdrift beaches, management of sediment on this regional scale. How can we get there? What can we do? So we tried a bunch of different things, but the routine that we've settled on is first to apply what's called a topographic position index. And so that is borrowed from the geomorphology literature, where typically you're working with real elevation data here. But since we have sort of this quasi elevation data here, what we can do is take that same approach, which uses like a windowed approach. It says, okay, what are my neighboring cells? What's my topography? Or in this case, what's my raster value relative to those other points? And can I start to classify the terrain based on that? Can I lump things together, basically? And so that's what it looks like if you take just this TPI to the NDWI values. And next, please. Then what we noticed is, okay, this TPI is a good first cut, right? You can see that outer ebb shoal, for example, in the image, right? That sort of green semicircle out there. But there's a lot of speckles. So we can take a despeckling routine and kind of take away some of those random green points that are out and likely associated with wave breaking. And then next, please, Ian, thanks. We can also take what's called a multi-ATSU image classification, right? So this is just another image classification approach. ATSU classification is pretty common in the coastal remote sensing literature. And this can help remove larger features such as boat wakes and helps lump things together even more. And so finally, next, please, we take the multi-ATSU and the TPI classes and kind of overlay those, and where those classified pixels are in agreement, we extract those shoal positions. And what that allows us to do, we'll see on the next slide, is start to make what amount to sort of like heat maps of where shoals are during different periods of time. And so let me orient you to this figure, but what you have is 4 different time snapshots where the top left corner is January of 2015 to summer of 2017, and then you have summer of 2017 to winter of 2020, winter of 2020 to summer of 2022, and then summer of 2022 to summer of 2025. And what we're seeing here is that the red values are where we have the greatest portion of shoal detection. So that's the percent of images that had that as a shoal area using that classification routine we just saw on the previous slide. And what that means is that we can get a general sense of over these windowed periods of time, where were shoals, and can we start to capture some of the evolution of the inlet over these multi-year time periods. And what we see here at East Pass, for example, is that there's in general a southeastward migration of that ebb tidal delta and a shifting of the channel position. And this sort of channel rotation is common at many inlets, but has been documented in the prior literature for East Pass, right, where a dredging cut may occur and then the channel kind of shifts back to the position that it wants to be in more naturally. And so the fact that there are these this good agreement between the literature and what we're seeing in our data was reassuring. But we went a step further, and so next, please. We were able to do these comparisons where we cast transects out of the center of the inlet from bathy data and kind of found the outer edge of the ebb shoal, and then did the same thing and then compared that to how it lines up with the outer edge of those detected shoals. And what we find is a pretty high correlation coefficient here, right? We've got R-squared values for most of these inlets that are in the upper sort of 0.8 to 0.9 range. So fairly good one-to-one relationships here in terms of the ability of this routine to actually detect shoal features. So I'll show you on the next slide another example also from Florida Gulf Coast. Here we're in the west portion of the main Florida peninsula at New Pass. And again, we're looking at the same thing. We've got 4 different windowed periods of time, right, where they're each just because of the same periods of time as on the last slide. And here we're looking at portion of shoal detections again. And what we see is those red areas are where shoals are more likely to occur. The blue is where they're less likely to occur. And what we see here from the New Pass data, there aren't as many clear trends in the migration of the ebb tidal delta itself, but instead there's a lot of internal reorganization going on and some channel migration, which is consistent with bathy data that we've analyzed actually as part of another CIRP work unit where we looked at bathymetric LIDAR and seen some of the same things play out over about the same time period. And so again, we've got 2 very different methods of looking at shoals showing some of the same things. And so I think this lends credence to this emerging approach. And again, we did that same comparison between the actual bathy and this satellite-based approach for shoal detection. We see really good agreement. And in fact, this lower R-squared value, despite the water actually being clearer in general here at New Pass, is a result of sort of the skewness of this ebb shoal kind of down to the southern shoreline. And in fact, the ebb shoal itself doesn't have a very good expression to the north. And if we drop those 2 northernmost transects in our analysis, the R-squared value gets into the mid 0.9s as well. So it's really just like 2 of those transects that are kind of driving this slightly lower R-squared value. But regardless, it's a very clear, strong relationship that makes us feel confident that we're actually seeing the real shoal dynamics that's occurring at these inlets. And then next steps for this portion of the multispectral work is that Copeland and the team have put together a Python Jupyter Notebook based workflow, and that we're hoping to submit this ideally to the journal Geomorphology at the end of the FY. So in, basically about a month from now. we're hoping to submit this work and get it out into the broader literature, as well as kind of release the workflow that we've been using for this. With that, I'm going to turn it over to Alex Ostoich, my colleague, who's been exploring some other next steps for this part of the project.
Thanks. Okay, so I'm going to talk about a few different analyses that we're looking at implementing into our kind of final tool from this project, and some different bands and band reflectance values we're using. Everything I'm going to talk about is not really final. This is all, still very much in kind of the testing stages for the final tool that will be coming out when we complete this. So for this, when you talk about some band ratios and space-time cube trends, pivoting from NDWI to test different bands, this space-time cube result is using the blue to green reflectance band ratio. And this ratio is commonly used in satellite bathymetry, particularly in the STUMP, the ratio model originally. And it works in these bathymetry applications because the blue and green bands both penetrate through water. However, green does have more absorption by water and it absorbs faster. So the deeper you go, the larger this band becomes proportionate to the depth. And that image of Barnegat Inlet from 2021 is just a sentinel image. Visually, you're looking at that ratio. I know I was just talking about the blue to green ratio. I'm going to kind of flip it on you. We're looking at green to blue, and that is done for the space-time cube analysis, just to more mimic a kind of bathymetric map where shallower areas are in fact higher as opposed to lower, for the sake of like it being a little bit clearer visually. So one of the kind of series of products we're looking at for the tool is some products from a space-time cube. We've talked about space-time cubes a little bit in this like kind of CIRP project ecosystem this year, particularly with, Scott and Charlene's next gen volume change project. Just to kind of reiterate, it is basically just a data format where you're stacking surfaces in a time series. So you can use this kind of then 3D cube to pretty easily look at trends in your data, look for hot spots, and get any stat values, etc. So you can go to the next. So this is an example of a space-time analysis I did for Barnegat Inlet. For this, we collected images from 2016 to 2023. There were 37 sentinel images in total, processed with the open source Acolyte software, which compared to just sentinel surface reflectance processing, this one is more tuned to kind of water environments. So this is something we are testing compared to sentinel processing to see what we're going to end up using in our final product. So this is just some examples of products we could put in our tool based on space-time cube analyses. The first two graphs there just show part of what we're playing with, an interactive capability where the user can, the tool can create this cube and the user can either look at transects or specific pixels to look at the ratio time series as well as time series of transects. What we're looking at here is just complete raw ratio values, so they are very noisy. If we do include something like this, we will be looking to add some type of smoothing just to have it be kind of a better visual. To kind of reiterate from the whole thing, this is very qualitative because this is just looking at the ratios. We're not actually giving any depth values here. So this, would be, you're going to look for trends and major changes. But, we're not adding any like numbers to this that actually would be more than just this is a ratio value that is a proxy for depth. And then the bottom is just some stats and trends. The first one is just the mean ratio value for the whole study period, showing areas of the strongest shoaling for that entire time. The middle there is just the standard deviation showing areas of variability. And then the last image is showing trends on Barnegat Inlet from 2016 to 2023. Yellow is an increase in shoaling, blue is a decrease in shoaling, which has shown pretty promising results looking at trends like this in the shift of particularly that ebb shoal and a little bit of a wiggling, I'm going to say, of the inlet shoal at the site. to move next. So another thing that we're looking at is actually using some satellite bathymetry algorithms to try to of using the indices and instances alone. Couple caveats before I, go further into this. If we could get this to work decently, this would not be something that the tool has a universal capability to do. If you're applying SAT-BATHY algorithms, you would need to, calibrate it to each individual site you're looking at for the best results. But if we could get it to work decently, we would be interested in potentially including capability like this in a few select inlets, perhaps some of the more managed inlets and our case study locations like Barnegat in the tool. And then hopefully this might be something that we could iterate on and add to in the future as needed or as wanted. So to test this, we're first using the STUMP ratio model, which uses that blue to green ratio that I was looking at for the space-time cube analyses. Basically, this takes the log of the blue and green reflectance values, and that turns the exponential kind of decay of reflectance through the water column linear, and then does a linear regression on it to get estimated depths from ratio values using real measured depth values. This model has been shown to have pretty decent accuracy in like clear water up to like roughly, I believe 25 to 30 meters. In more murky areas, the linear relationship falls off a lot quicker. But to test it, we used Sentinel imagery, which the bottom left image there is just an example of Sentinel blue-green ratio image from April 18th, 2017. And then that was compared with eHydro depth measurements from April 14th, 2017 in the area where eHydro depth existed, which is just that inlet channel. To add a little bit more accuracy, I guess, or to test rather how accurate it would be. In addition to that, I kind of filtered the data before I put it through the linear regression. Basically, every point where there was a depth measurement, we extracted and took the ratio value at that point, and then those points were additionally filtered by all the points that had a higher than 50% NDWI value, just to see if we can get it to be a little bit more accurate than using all the points. And then the chart showed result examples from kind of the first test round of this. The first chart shows the ratio compared to the eHydro actual measured depth values with an R squared of 0.8 and a root mean squared error of about 3 feet. And below that shows just the estimated depth values versus the measured depth values from eHydro. Has decent correlation, but it does fall off at roughly about 20 feet, which is only about 6 meters, using this test case at Barnegat, which makes sense considering it's not quite clear water and the picture perfect site where this works further down. Keep going. So using that kind of first test case, these are just some of the results that we got out of it. For Barnegat Inlet, I was interested in isolating everything using the results from that model that was above 10 feet mean low water as being the authorized depth at Barnegat. The first image there just shows a really good extraction, but it was, pretty clear edges, pretty clear extraction of the Inlet Shoal and the Ebb Shoal. And the two stacked images show the results of the STUMP extraction from 2016 to 2023 using the same imagery that was used in the space-time cube analysis. Now, these are just raw first pass showing promising results. It's still evident that some suspended sediment is likely caught in some of these areas. And no error at this stage or kind of tidal effects are included. And that's something that we would also want to account for somehow if we were to output results like this or use this. You can continue next. Some of the next steps for this section, in terms of data quality, this is something that that's in progress. What we're doing is we are kind of taking all the indices and band values that we're using in DWI, blue, green, blue, and we're comparing it with actual depths that we're getting from eHydro to kind of better estimate overall error and be able to better kind of describe what we're working with and how these depth proxies should be viewed as compared to, what your actual depth might be. In addition to that, we're comparing, as I had mentioned, different post-processing algorithms, the Acolyte software versus just the Sentinel Centicore surface reflectance processing that they do straight when you download the Sentinel image, to see which one works better for our coastal water application. For the space-time cube, what we're looking to do is kind of identify what could our final products be on that for our final tool, what stats, what trends are important to users, like do we want to show yearly, seasonal, etc. And in addition to that, we're looking into smoothing that raw reflectance data in order to kind of produce clearer qualitative results with those trends. And then with the satellite bathymetry, we are considering that was the first test. There's quite a bit that we want to do in that area. We want to test that regression on points with kind of various filtering methods. For example, what we're interested in kind of testing is taking that multi-Otsu threshold filtering that was used in the shoal extraction method that we initially outlined, and then use that, and then on top of that, satellite bathymetry to see if that can improve, the final results. What we're going to do with that is compare any extracted areas we have with polygons extracted using depth values from eHydro to see how our surfaces compare. We're going to test models that kind of iterate upon or add to the STUMP algorithm to see what results we can get from various SAT-BATHY algorithms. And then in addition to that, we would want to integrate an error range into any final product, as well as kind of look into how we might be able to incorporate tidal ranges in what we put out from that. And then we can go next, and then I will pass it back to Ian.
Thanks, Alex. Great work to the team over there. Really exciting stuff. So now we're going to transition over to the wave-dominated approach. And I'll just highlight here that both of these teams were fairly early on in the projects in year one, finishing up year one, basically. So it's very much in the R&D phase. And similar to Alex, some of this data you'll see here is more in a qualitative state, but I think the long-term goal is to, complete these sort of R&D steps and then eventually combine forces into one sort of toolkit that will be best sort of catered to your site. And so we'll, down the road that might live in ARC, perhaps somewhere else. That's a discussion point for the group. So moving on here, I'm not going to spend too much time on the COSAT algorithm itself, but it was originated in Australia, the University of New South Wales, I believe, in 2017 or 2019, and it leverages commercially available satellite imagery. So as the past group talked about, we have this incredibly rich data set that's freely available, dating back to 1984 if you're using Landsat. And then Sentinel came in both at 10-meter resolution. So with those publicly available satellites, we can have a combined revisit rate of between 5 and 16 days. And then we've also been investigating higher resolution Planet Labs, Planet Scope imagery that's available since 2016. That's 3-meter pixels. So just real briefly, COSAT uses supervised classification to classify into sand, whitewater, water, and shoreline. You can see in this top center plot. It uses the MNDWI, Modified Normalized Difference Water Index, and a thresholding algorithm to pick out your water line where the water and land meet. And from that water line, then it converts, tidally corrects, and uses the beach slope that's either user provided or calculated to give you a shoreline based on a vertical datum. We've tested a lot of the accuracy at sites across the country for the shoreline portion. Generally, you can expect somewhere in the 10-meter RMSE range. So past work focused on translating that sort of Python base, which required some expertise, into a much more user-friendly ARC tool. This is available on the CIRP website. And it's supposed to be a pretty simple tool. You just provide an AOI shapefile, your time interest, whether or not you know the slope, your transect spacing, etc. It runs fairly quickly, and then you have your time series of shoreline at your area of interest. We created some additional products for the user, like these linear regression point shape files, and you can zoom in then on a specific area to look at your shoreline behavior through time. So this is just showing how the shoreline evolved from 2019 through 2022 at this location in Duck. So I encourage you to check that out. The next phase of this, right now, we're working on migrating beyond just an ARC tool to a more widely accessible web portal. We're calling this NatSat. So you can go to anywhere in the country and look at your historic data, and then also it will populate your most recent shoreline, and we'll have more analysis products like that. So that is ongoing on the shoreline front. We're going to switch gears now and talk about how we can exploit the classification of the whitewater now for shoal extraction and detection. So originally they chose to classify whitewater to sort of constrain the area of interest for your shoreline and to reduce error. But right away we realized, well, we can probably use that for more than just reducing error for our shoreline. We could probably use that in our inlets themselves. So we've done some storm response work with the satellite tool, and I'm just highlighting here some results from Florida after their 2024 hurricane season. And you can see these plots to the right show that the pre-storm on the top right and post-storm on the bottom right, there's these new breaches that formed. And so with just this alone, you can get an idea, of storm impacted areas, perhaps the extent of your inlet, and then furthermore, how long it takes to close, etc. So using that whitewater, we're going to talk about a couple sites today in more detail. And so as both groups sort of combined forces, as we've mentioned, and we chose our first pilot site of Barnegat Inlet in coordination with our PDT. And so here's an example of just a nice whitewater classification highlighting this ebb shoal at Barnegat on the top. So let's look a little closer at this data set. So this horizontal plot at the top is just meant to show you the frequency of satellite imagery. So we've extracted imagery from 2000 to present, and that's a total of over 1,500 Sentinel-2 images. And then we've overlain the available ground truth by these orange boxes. And so a few things to note there. There's a lot of satellite data, not so much ground truth data. This, I would say, is a site that does have more available than a lot of our district inlet sites. And so, again, we have sort of minimal chances to compare our results. But today we're going to talk about where we're at with a couple of these surveys from 2005, shown here on the left. The Bathy data is in the grays, and then a survey from 2022. Something to note here right away is the difference in survey coverage. So this was much more comprehensive. This went out into the open coast and also into the back bay, whereas this one was just focused on the ebb shoal itself. So if we take a closer look, this is just sort of, again, a bit qualitative at this stage, but we're comparing the ground truth extracted shoal. So anywhere that's under 3 meters of depth, that's in blue. We're comparing that with our Sentinel-2 extracted whitewater, which is a proxy for the shoal itself. And so comparing the extents of the blues and the orange here, you can see there's fairly good agreement. We would expect the agreement here along the shoreline where the waves are breaking. It deviates probably most here along that shoreline, and then this shoal that's tucked along the backside of this jetty. But we are pretty pleased to see the agreement out here as we move into the ebb shoal. A really important point to highlight here is the bathymetry survey did not cover the ebb shoal entirely. So again, the satellites offer a much broader glimpse at what's happening at this rapid scale, and so we've actually been able to classify this shoal out here farther than the survey itself went. Just another comparison from 2023. Again, there's fairly good agreement here in the position of the shoal. So the ground truth derived shoal is in blue, and the sentinel derived shoal in yellow. It's a little misaligned here, but generally, happy to see that it's detecting this shoal presence within the ebb shoal extent here. So we're going to elaborate on this to create some statistics, and compare our areas, and also look within the inlet throats in the back bay as well. So that was Barnegat. Now let's take a closer look at Oregon Inlet. Oregon Inlet, notorious for hazards, a lot of groundings here. There's a terminal groin on the south side here, but there's no jetties. To the north, a pretty contentious area. So there's highly dynamic shoals, a lot of sediment transport, high wave activity. So this is a pretty fascinating area to study in more detail. And so this is a date from January 2025. And here is just a movie showing the the classification from 2017 through the modern. And I think what you can notice here is the variability in that shoal position out here in the open coast. Again, some of this is a product of when we have high enough waves, but you can also see the variability in the shoal within the back bay here as well. This is the bridge running across the inlet, if you're curious. So this instills some confidence in the ability to first detect the white water in this area. So then what we've been doing is zooming in on individual pixels to sort of similar to the last group, to look at the probability at each precise location on shoals existing in the past when waves exceed a certain threshold. So if we only extract imagery when waves were greater than 1.5 meters, we've created this heat map or probability map. And this is, again, the reds are showing your probability of whitewater or shoals. And so it's doing a nice job at really outlining the predominant extent of the shoal. Of course, the shore break, but then it's also highlighting some of these more shore oblique oriented features beyond the inlet throat itself. You can see the fainter reds. This shoal is a bit more dynamic back here, but you can see it's picking out the shoal in the back bay as well. It's also highlighting I think the change in island configuration over time. Again, these inlet limbs fluctuate significantly, so this landmass itself has changed over time, as shown by the reds on the base map. If we do the same thing, we can create a probability or heat map for Barnegat. So we have lower probabilities of shoals here, but we can see that this is, again, doing a nice job at outlining the extent of that ebb shoal, probably a little farther than I would have expected it out here. It's faint, but again, it's showing that, yes, we can classify the whitewater here and sort of detect shoal presence in this environment. So that's sort of covering the COSAT side. Now we're moving on to sort of the next phase. You notice the ground truth comparisons from the first one are months apart. That's a product of a few things, just the availability of ground truth. We need wavy conditions, we need cloud-free conditions. So there's some critical factors here that sort of are limiting us. And what we've noticed that here's an example to the right is that the COSAT again, it's geared and trained to pick out the shoreline, right? Not the whitewater necessarily. So we've noticed that it's often under classifying the whitewater. Here's an example where it's clear there's clearly waves breaking out here, but it's not really detecting all of that. So our question is then, can this be improved with a more sophisticated supervised classification model? And so briefly, COSAT uses the multi-layer perceptron neural network to classify, again, just as 4 classes. This was trained on a fairly small data set, 50 images with Sentinel and Landsat, 25 on PlanetScope. Those are shown here to the right. And so we've brought in Clay Caldwell. He's working with several others in Vicksburg. We're lucky to have some of his time to sort of lead the charge here on helping us test another classifier. So Coast Train was created by the USGS a few years ago. And the idea with Coast Train is let's bring in more images from broader environments to see if we can better classify some of these coastal systems, even non-sandy areas, back bay areas, etc. So Coast Train used 400 plus images. So right there, that off the bat, that's a perk. And so what Clay has been doing is using those 400 images to test the accuracy of the traditional COSAT approach using that multi-layer perceptron, or MLP. He's making some good headway, but right now it's only at about 55% accuracy. And so, existing COSAT still is currently more accurate, but this 99% is a little deceiving because it's, again, focused in on that shoreline. So we're thinking that there's just not enough whitewater pixels generally in these training data sets. So we're trying to incorporate more imagery and sort of improve on this 55% here. Clay is also very excited to be developing a CNN here that I think is going to take us a step in the right direction. And with the CNN, the main benefit here is you can really learn from the image as a whole, as opposed to just the individual pixels. You can learn about the relationship between the location of a labeled feature and an image and its surroundings and the info stored within the imagery. And so with these extra labels, also, as you can see here, extra classes, we could also apply this in more diverse environments, perhaps moving beyond just sandy coastlines into like a marshy area. So yeah, this is pretty, these are fairly new results here. So we're eager to continue on this path. You've seen some of our sort of analysis products in the works here. Here's just a mention of another one. We're hoping to develop some directional vectors and migration rates. This is just a mock-up, a hypothetical situation, where you would have a arrow showing the dominant migration. Maybe its length is reflective of the rate or something. And so with this, you can start to understand perhaps your broader sediment budget. You can couple this potentially with your shoreline results to have a much better sense of where your sediment is moving. All right, so with that, I think that was a lot of material. We have about 13 minutes, and we, I think, can open the floor. As a group too, we've come up with some questions here to sort of drive the conversation. But with that, happy to answer any questions or take any feedback. Thank you.